record this. Okay. So start a new note. Oh, what's your name? Grace. All right. So for how I mark, I'll start with 100%. So I don't build you up to 100%. You start at 100%, and then I dock you marks. I find that that saves you some marks in the end because there's always some bogus marks in there that kind of everyone gets. Okay. So I find that it's a kinder way to mark, just kind of docking marks as I go. Okay. So this is, oh my goodness, it's October. That is crazy. All right. So assignment number 1 is marked. Okay. And if you see something like -0.5, this is always -0.5. It's not 1 out of 2, it's just 0.5. Okay. -1 is just -1, etc. Okay. I've tried to write little notes as I go along. You might see things, sorry, there's an echo in the iPad, and it's probably only going to bother, well, like us 3. But I can't figure out how to mute it. So you might see things like, okay. Okay, what does okay mean? Okay can mean lots of things. It's kind of my very flexible, like sometimes it's okay, or sometimes it's like, oh, okay. So it just depends on the scenario. Often it's something like you're not quite there, right? But there's not enough missing for me to dock marks. Okay, so that's okay. It's worth looking into what's missing, right? So I'm just making a note that, okay, you're almost there, right? Or another scenario would be if you got the wrong answer, right? So if you were doing this assignment, for example, and you got the wrong 3rd quartile, right? We use the quartiles to find the 1.5 interquartile range, right? So then how are you supposed to know that you did it wrong, right? And so, so then if you use the quartile that you found to find your interquartile range, then I just followed through. And so then it's not right, but it's okay, right? Because you followed through and everything's good. Okay? So okay can mean kind of lots of things, right? So okay is kind of almost right, or given earlier work, you followed through. So some of those, if you ever have any questions, then just ask me, okay? But we'll wait till after class if you have questions. Okay? No lab on Friday. No lab on Friday. I'm out of here. I don't know about you guys. It's Thanksgiving. Get out of here, guys. Or maybe stick around, but don't do anything in the morning. So no lab on Friday. Okay. Oh yeah, any other questions? Burning questions like that? You'll get assignment 2 on Wednesday. Okay. Yeah.
Is there going to be kind of like, I haven't really looked on those, is there going to be a practice midterm for all the 27?
Yeah. So before all the tests, you will have a practice test, and we go through it together in the review class before the test, right? So you'll have lots of time to review stuff. Okay. Say that again. Yeah. Like, you got it. Any other questions? All right, let's get going. So, if you didn't get your assignment, you can pick it up after class because I don't want them. I end up lugging these things around. If you need a formula sheet, I brought some extras today. So, and also if you want blank assignments that I've printed off, you're welcome to them. They're done now, so they're not much use to us. But if you do want an extra one, then you can grab it. Okay. So, for review, it was a long time ago that we were here. We're going to review by example. Okay. So, let's see here. Where was it? Oh, I put it at the bottom. So I'm just stealing this out of the textbook. The textbook? There's no textbook. Well, there is and there isn't. I steal examples out of it. Oh. Big example to steal here. Okay. We're actually not going to do that much, so you don't have to copy this all out. I'll give you the information that we need from it, okay? But just to give you some background, so we're talking about smallpox, okay? So smallpox in Boston, and so we're looking at 6,224 individuals from 1721, so a long time ago, obviously, who were exposed to smallpox in Boston. So doctors, of course, believed in inoculation, which involves exposing the person to the disease in a controlled form, right? And then they thought that if you've been exposed to it, right, then you have the antibodies and then you can fight it off when you actually get it. Okay. So each case, right, each case is a row in our data set, right? So each case represents one person with two variables. Either they were inoculated, right, yes or no, and the results, did they live or die? Okay. And so we have this contingency table. Really, if you're going to copy anything down, I know, now I tell you, right? Copy this table down, okay? It's the table with all the results and each of the probabilities instead of the raw counts. Okay. There's no question here. I know, don't worry about it. I'm gonna zip back and steal the question that we want. We'll do this one just for fun. It's not the one I was gonna do initially. So I know you guys are working on your table still. But the first thing that we're going to do is write out informal notation, write our probability notation that we've been working with. The probability a randomly selected person who is not inoculated died from smallpox. and find this probability. So we have lots of probabilities here. Okay. And so what we want to find is the probability, oops. The probability, actually, we need to establish some things before I go and use the shorthand, right? We can talk about the results, right? Which is either they lived or they died, or they lived it or they didn't live, right? Or they were inoculated or they weren't inoculated, right? So we can let, oops, L be the event that they lived. So the complement of L, we talked about, the complement of anything is just not whatever it's talking about, right? So I'll say not lived, right? Meaning they died. Just to use that not terminology. Okay. And I can mean that they were inoculated. So the complement of I would be not inoculated. Okay. So what do we want to know? We want to know that the probability of randomly selected person who was not inoculated, right? So just make a note here. So not inoculated and died from smallpox, right? So we want to know and died from smallpox. So that means they didn't live, right? So if you write out the question like that, right, then we can just put probability notation around here. So now, for this question, right, we can just look at our table that you've copied out, right, the one with the probabilities, okay, and say, okay, well, what's the probability that they, what did we say, were not inoculated, right? So they're in this column, and they died. So to be in this column and they died, so the probability is 0.1356, right? So we just steal it from the probability table. How about something a little bit more involved? So now, let's say that we're only given two pieces of information, that 96.08% of residents were not inoculated, and that 85.88% of the residents who were not inoculated ended up surviving, right? So now we have this conditional probability, right? So we know that they were not inoculated, and of those, some amount ended up surviving, right? Or they lived. How could we compute the probability that a resident was not inoculated and lived? Okay. So I'll just steal our table here. So we have it. 85.88. So from our blurb, right? This is what we know, but I guess the question says, given only those two probabilities. So we don't actually need this table. Oops. I'll cut it, save some space. Didn't go anywhere. Just to undo all my text first. Okay. Oof. All right. I keep wanting to refer back to the table, but we're only given that the probability of not being inoculated was 0.9608. Right, 96.08%. We convert it to a decimal to use it in any sort of math that we do. So 0.9608. And we're told that were not inoculated, and 85.88% of the residents who were not inoculated ended up surviving. Right? So really how we write that is, I'll start slow here. So first they were not inoculated. Can't spell inoculated. And then they lived. So it's the same as the probability that they lived given, remember that notation? Given that they were not inoculated. Or in shorthand, we can say the probability that they lived given the complement of I, and we're told that that's 0.8588, right, or 85.88%. As a rule, right, you don't want to round anything really, unless it's absolutely necessary. And if I give you accuracy to 4 decimal places, you should be returning accuracy to 4 decimal places. Right? And so I'll just make a little note here. When given 4 decimal places in the question, your work should have at least 4 decimal places. Right, so we just keep the number of decimal places that we've been given. We don't want to ditch them, right, until potentially the very end. Okay. So what do we want to do here? How can we compute the probability that the resident was not inoculated and lived? Okay. So we want to find, find the probability that they were not inoculated and that they lived. So we have these two pieces of information, right? The probability that they lived given that they were not inoculated, and the probability that they were not inoculated, right? And so we know from last day, I know it was a while ago, but also from your formula sheet, right? The probability of A given B is the same as the probability of A and B over the probability of B. Right, that's how we're going to work with conditional probabilities. This is a given. So we know the probability of L given that they were not inoculated, right? And we know the probability that they were not inoculated, right? And we want to find the probability of, well, we said not inoculated and living, but if we rearrange those, right, doesn't matter. That's living and not inoculated. Order doesn't matter. Okay. So since the probability of not inoculated and living is the same as the probability of living and not inoculated, right? Order only matters with the given sign. Okay. We set up the following. The probability of L and not I, right, or the complement of I, can be written as the probability of L and not I over the probability of not I. Okay. We know, oh, I have a typo. Should be the probability of L given that they were not inoculated. Sorry, it's Monday morning for me too, guys. Been here a while, but still a little soggy. There we go. Right, and so we know this one. We're told that this is, what were we told? 0.8588. And we were told that the probability of them not being inoculated was 0.9608. We have to find the numerator. Okay. So we know that 0.8588 is the probability of L and not I over 0.9608. Multiplying both sides by 0.9608, we get 0.8588 times 0.9608 is the probability of L and not I. Point 0.8588 times 0.9608. We get 0.8251354 is the probability of living and not being inoculated. I'd say they're pretty good odds. Or if you want to round, just go to the probability of L and not I is 0.8251, right? Keeping 4 decimal places at least. Okay. Just because that's how many I gave you. Any questions about that one? I'll steal the example first. That one. So this is the end of our review. Okay. And to finish off our probability section, sometimes it's going to be easier to lay these things out as tree diagrams, okay, where we have, okay, something happens first, right? Either they were inoculated or not, and then either they lived or they didn't, right? So each of those represents a layer of branches, right? So making tree diagrams is going to make it easier to calculate some of these probabilities, or at least to visualize the combinations. Okay, so probabilities with tree diagrams. Oops. Diagrams. So I like this example because it's easy for us to kind of see the progression, right? So, so consider the midterm and final for a stats course. That's us. Suppose 13% of students earned an A on the midterm. Okay, so you either got an A or you didn't get an A on the midterm. Okay. And of those students who earned an A on the midterm, 47% received an A on the final, and 11% of the students who earned lower than an A on the midterm got an A on the final. Okay. So we have this scenario where first you write the midterm, either you got an A or you didn't, right? And then regardless, there's going to be another set of branches on either one of those branches, right? Where you write the final and you either get an A on the final or you don't. Get an A on the final or you don't, right? And so we have this tree of probabilities. So first we're going to need to talk about, okay, so we get an A on the midterm. So we talk about the midterm, and then we talk about the final, right? And because we're talking about A's in both instances, right, it's not going to be very handy to talk about A and not A, and then A again and not A, right? That doesn't make sense. So we're going to say let M be getting an A on the midterm, and F, kind of counterintuitively, getting an A on the final. On the final. Because we need notation for each of these layers, right? First you write the midterm, there's some outcome. Then you write the final, there's some outcome. Okay. So what it's going to look like in general is we're going to have our first layer. We'll call this our midterm layer. And then from here, each of these branches has its own set of branches. We'll call this our final layer. Or in the case of the previous example, right? You were inoculated, yes or no, and then you survived, yes or no. Right? Okay. So without writing down the probabilities quite yet, we can label each of these branches, right? So we're going to say, okay, either you got an A on the midterm or you didn't get an A on the midterm. Leaving some room because we're going to write each of the probabilities for each branch underneath. And then, so following the, you got an A on the midterm, then you could have got an A on the final or you didn't get an A on the final, right? So you got an A on the final or you didn't get an A on the final.
Why is it just a tick instead of a C?
Oh, thank you. That's me falling into my old ways. It's the complement. Sorry, guys. I should be writing C. Usually C's end up being too much work, so we do little primes instead. Thank you. Keeping me honest up here. And then here, let's see if I can stick with it though. Either you didn't get an A on the midterm, but you could have gotten an A on the final, right? Or you didn't get an A on the final. So before you start kind of untangling all these probabilities in the word problem, right, then it's helpful if you just identify the layers of the tree diagram. And I'll say, you might find a tree diagram helpful, or I might even say, make a tree diagram, right? So then your first step is to identify, okay, what are my levels of my tree diagram? In this course, we're not gonna go more than 2 levels. In theory, you could go an infinite number of levels, but that gets out of hand real fast, right? So each one gets, right? You can even start with more than 2 branches, 4 branches. Each gets 4 branches. Yikes. Okay, so now, at least when we have it laid out like this, now we can start pulling these probabilities from the word problem and say, oh, okay, well, that's going to go in this branch, and this branch, and this branch. Okay, so let's go back here. So suppose 13% of students earned an A on the midterm, okay? Meaning the probability of getting an A on the midterm is 0.13. Okay? So the probability of an A on the midterm is 0.13, meaning the probability that you didn't get an A on the midterm is 1 minus 0.13, 0.87. Now we're told that of those students who earned an A, so now we know that we're only talking about those who got an A on the midterm, 47% received an A on the final. Okay. So now we know that, okay, we're down this M branch and 47% got an A on the final. So we have 0.47 down here. And each set of branches has to add to 1, right? So we have 1 minus 0.47, 0.53. So 53% of those who got an A on the midterm didn't get an A on the final. Okay. And 11% of the students who earned lower than an A on the midterm received an A on the final, right? So now we're down this, they didn't get an A on the midterm, but they did get an A on the final, and we have 11% there, so 0.11. So 1 minus 0.11. Don't try to be a hero here. Use your calculator. 0.89. So now we know that of those people who didn't get an A on the midterm, right, 89% didn't get an A on the final either. Okay. So these probabilities in the second layer, right, they're conditional probabilities, right? So the probability of getting an A on the final, given that they got an A on the midterm, right? Not getting an A on the final, given that they got an A on the midterm, right? So these probabilities are all conditional probabilities. Okay. So I'm just gonna, I'll zoom in on this one. The probability of getting an A on the final, given an A on the midterm, we're told is 0.47. Showing that the second layer of the tree diagram, the second layer of the tree diagram is conditional probabilities. Probabilities, if I can squeeze it in there. So now, if I want to know, find the probability of M and F, so getting an A on the midterm and getting an A on the final, we know we have conditional probabilities, so we could write it out in terms of our notation, right? The probability of, oh, you know what? I should reverse these. F and M. Let's see why in a sec. The probability of the final given the midterm. Oh, sorry. Oh my goodness. Half asleep up here. Scratch all that. I know. Sorry, guys. We know that the probability of F given M is the same as the probability of F and M over the probability of M. It's because I was trying to use the reworked formula without giving it to you. Right? We can rework this by multiplying the probability of M over to the left-hand side, right? And then we have a formula for the probability of F and M. We mentioned it last day, but we haven't mentioned it since. So the probability of F given M times the probability of M is the probability of F and M. So find the probability of F and M. Phew. Thanks. This is all just to show that to find the probability of F and M, we end up just multiplying down the branch. So that's the same as the probability of F given M, right? Which we said was the 0.47, so the bottom branch, and then times the probability of M, which is the top branch. Right? So the probability of F and M, I'll just rewrite it with the probability of F and M on the left-hand side, is the probability of F given M times the probability of M. Where this, right, is the lower branch, and this is your top branch. So we said that the probability of F given M, right, was 0.47. And the probability of M was 0.13, right? Getting an A on the midterm, 0.13. Okay. So 0.47 times 0.13 is the same as 0.13 times 0.47. So we have 0.47 times 0.13 is 0.0611. We don't need to use those formulas all the time, right? And that's nice because now we see that to get the probability of the first branch times whatever branch we want in the bottom, right, we can just multiply down. Right? So to find the probability of a, let's call it a stream of branches, really getting natural here. A stream of branches, right? For example, the probability of M and F, the probability of M and not F, probability of not M and F, and the probability of not M and not F, right? Those are all our possible streams that we could take going down our tree diagram. Okay. So to find each of these probabilities, right, we simply multiply down the branch or down the stream. We multiply down the stream of branches. Okay. So looking at the probability of M and F, right, is 0.13 times 0.47. Probability of M and F not is 0.13 times 0.53. Not getting an A on the midterm and getting an A on the final, it's 0.87 times 0.11. Not getting an A on the midterm is 0.87 times not getting an A on the final, 0.89. Right. So we can just multiply down the stream. So I tell you, okay, so you have a student and they didn't get an A on the midterm and they didn't get an A on the final. What's the probability of that? Right, that's going to be 0.87 times 0.89. Right. So now you know those probabilities, right? So we can just multiply down to find all those total probabilities. Okay. Oh, there is a question in here somewhere. So we've set up our tree diagram, and then you randomly pick up a final exam and notice the student received an A. Okay. So now we know that this student got an A on the final. Right. What's the probability that this student earned an A on the midterm? Right. So for the question, I'll just reword it here. Student got an A on the final. What is the probability that they got an A on the midterm? Was that it? Yeah. What's the probability they got an A on the midterm? So we know they got an A on the final. Right? So really what we're saying is the probability, what's the probability that they got an A on the midterm, given that we know they got an A on the final? Okay. Using our probability notation, right, we can reword this as the probability of M and F over the probability of F. We already know the probability of M and F, right? We said, okay, we can either multiply down the branches. So M and F has to be 0.13 times 0.47. So M and F is 0.13 times 0.47. Over the probability of just getting an A on the final. Right. So just getting an A on the final, right? That can happen two ways. You can get an A on the final here, right, where you got an A on the midterm, that's good. But you can also get an A on the final here where you didn't get an A on the midterm. Right? So when we have these two scenarios, right, we find the probability at the end of this branch, right, the probability of M and F down here, and the probability of not M and F down here, and then we can add them up, right? Because the probability of getting an A on the final, right, just in words, is the same as me getting an A on the midterm and getting an A on the final, or the probability of not getting an A on the midterm but getting an A on the final, right? So we need to find the probability of F. Right? we can get an A on the final two ways. Oops. Midterm and F. I'll just put brackets around it. That's one event. Or I didn't get an A on the midterm, but I did get an A on the final. So one little trick that I want you to keep in mind is when you're saying and, we end up multiplying things, right? So we end up multiplying down the stream, right? Midterm and final. If we're saying or, then we're adding things, right? So and means multiply, where or means, bless you, means add. So what we can say is the probability of of getting an A on the final F is the probability of M and F plus the probability of not M and F. Probability of M and F, we said was 0.13 times 0.47 plus the probability of not M, 0.87 times F, which was 0.11. So 0.13 times 0.47, 0.0611 plus 0.87 times 0.11, 0.0957. So adding these two up, plus 0.0611, 0.1568. So now we know that the probability of getting an A on the final, regardless of what happened on the midterm, right, is 0.1568. Now we can solve and say that, where were we? The probability of M given F is the probability of M and F, just again, over the probability of F. We know from up here, right, the probability of M and F is 0.13 times 0.47. Oh, there we go. 0.13 times 0.47 over 0.1568. .13 times 0.47, 0.0611 divided by 0.1568. 0.38967, let's say. Oof. It's a lot of work for one question. Don't worry, you'd be rewarded with marks. Any questions about that one? So the tree diagrams are going to need some work.
So I had a medical.
Oh, yeah, don't worry. Yeah. You guys are welcome to come and go as you please. Okay, so that's tree diagrams, right? And once you kind of figure out that, okay, I can multiply down the stream to figure out the probabilities, and then I can add the end of the branches, right, the end of the streams together to find whatever probability I need, then they're going to be easier to work with. Okay. All right. Yeah. So the probability that a student got an A on the midterm, given that they got an A on the final, is 0.3896. If you want some more practice, you can try guided practice. So this is in the textbook, first time and potentially last time I'm sending in there. Try the guided practice 2.53 on page 97. Mostly because we don't really have time to go through another example together, right? But it's good to see more examples. Okay. So, just like that, we're finished chapter 2. Whew. I confessed already, chapter 2 is my least favorite chapter in the whole course. And now it's done. And we can put it behind us. Okay. So, let's get on to some more fun stuff. But any questions about probabilities in general before we get going? Okay. So we're going to move on to chapter 3. Can't remember what it's called. Sounds reasonable. I was going to say I could name it something vague, like the normal distribution. Okay, here we go. Thank you. Of course it's called. All right. So the normal distribution, we've talked about the normal distribution, right? We said that, okay, it's going to be this kind of bell shape, right? And we talked about how do we describe the normal distribution, right? We talk about the shape, the center, and the spread, right? The center for a normal distribution, we use the mean, and the spread, we should use our standard deviation, right, for our numerical measures. So we've already said that if we have a normal distribution, we should use the mean and standard deviation which if I'm going to write about it, I'm just going to shorthand it to SD. Now on. as our measures of center and spread, right? If I'm asking you to just describe the distribution, then you just eyeball the center, check out the range, right? What are some reasonable values, right? So, but for our measures of center and spread, we use the mean and the standard deviation. So as our measures of center and spread. Let's see. We need some notation, which we've already seen, right? But let's just bring it back up because it's been a while. So we need some notation. And if you get a handle on this notation, the rest of the course is going to be so much easier for you. Okay, I know that it's hard to get a handle on this notation, okay? But once you do, then you'll find that it's much easier. Okay? We're going to be talking about X bar, which is the sample mean. We're also going to talk about a single observation X. So a single observation, we just denote by X. Mu is the population mean. Lowercase s is the sample standard deviation. Sample standard deviation and a lowercase sigma is just an O with a tail on top, is the population standard deviation. And it must be something about how our brains work, but most of the questions that I get is because we refuse to recognize that there's two means and two standard deviations. And we just want to talk about one mean and one standard deviation, right? But as long as we keep track of, okay, there's going to be a mean and a standard deviation from the sample, but there's also a mean and a standard deviation from the population, right? As long as we kind of keep all those separate, then you're going to be way better off. Okay. So, get notation, terminology, lay in the groundwork. Let's throw a little fact in there. An LFF, a little fun fact. This one's just a fact. Regardless of the mean and the standard deviation, right? So the values for the mean and the standard deviation, regardless of the mean, and I'm talking the population mean, yeah, and standard deviation, and I'm talking the population standard deviation sigma. Yeah. The normal distribution will always be centered on mu, will always be centered on mu, and fit 3 standard deviations, so sigmas, on either side of the mean. On either side of the mean. Mu. Perfect. So what that's going to look like is something like right? So here's our fact, just graphically. We have a normal distribution. The normal distribution will always be centered on mu. So whenever you're drawing your normal distribution, and you will be drawing a lot of them, okay? So it's good to lay the groundwork here. The center line will always be representing mu, okay, your population mean. And then, just as a fact, we can fit 1, 2, 3. That one should have been a little bit closer. And then 1, 2, 3. Where each distance here is a distance of sigma. Oops. 3 standard deviations on either side of the mean, and a little bit. Okay. The reason is, technically, these tails go to infinity and negative infinity, technically. Meaning the curve never actually closes on the axes. Okay. There's always a little bit of room representing those very, very, very unlikely probabilities, right? Very, very small probabilities. I let the cat out of the bag, but the area under the curve is the probability. Okay. So we'll talk more about that, but for now, okay, we just need to talk about, okay, so from the mean, we can move out 3 standard deviations on either side, and then we've covered most of the curve. Okay. So at this point here, we've moved out to mu plus sigma. At this point, we've moved up to mu plus 2 sigma. Right? We moved out 2 standard deviations to the right. Okay. And here we've moved out to mu plus 3 sigma. Same idea on the ones below the mean. We've moved out to mu minus sigma, right? We moved down 1 sigma amount from mu. And we've moved to mu minus 2 sigma. And finally to mu, oops, minus 3 sigma. Okay. So this means that the majority, not all of the curve, the majority of the normal curve is captured between mu plus minus, right, to indicate that we're working on either side of the mean, mu plus minus 3 sigma. Right. Has anyone heard of 6 sigma in business? Anyways, it's referring to this, right? We've got 3 sigmas on either side, 6 sigma, covering all the possibilities, essentially. Okay. But if you haven't heard it, now when you hear about it, you'll go, oh, I know what they're talking about. Maybe not quite yet. Okay. So I will end here because we did a lot today, a lot of probabilities. And we'll start here next day. Cool. If you didn't get your assignment back, then you should come grab it. If you want a blank assignment or old assignment or formula sheet, you can grab that. Otherwise, I'll see you on Wednesday. Let's see here. I'll just stop.